To go over this paper by Edward Lorenz, and Lorenz is a pretty famous name, and I think you'll appreciate this paper because I chose it, and it's often studied extensively because it illustrates the idea of chaos and sensitivity in turbulent flows. So let's just look at it together, and you can read the whole thing, but I would like to go through and highlight certain things. So the first paragraph of your paper is very important. And usually when you read papers, I personally like to read the abstract and go look at all the figures and read their captions and try to understand them. And I never read a paper straight through. I usually read the introduction, maybe look at the results and read the conclusion, and then I might go through the whole paper. But I kind of went through and highlighted a few things I want to point out to you, which I think are important, so you get the most important parts of the paper, and then what we're going to do with the first class programming project. So deterministic non-periodic flows, when I read that, it means there's determinism. It's not stochastic or statistical, but all the statistical quantities of this simplified turbulent flow, if you will, could be derived if we wanted. It's non-periodic, right? So it's not really well suited to be attacked with Fourier methods. And it's a flow, of course. And he really focuses on a simplified model of an atmospheric flow. And it's very similar to a Rayleigh flow, which we'll note. So let's read the first part together. It says, certain hydrodynamical systems exhibit steady state flow patterns, while others oscillate in a regular periodic fashion. So those are the first two cases. Those are the easy ones. And still others, they vary in an irregular, seemingly haphazard manner, and even when observed for long periods of time, do not repeat their previous history. So that's the more of a turbulent flow. And we'll look at it through a dynamical series of equations. I've highlighted in my notes this little part of the paper, and it says lack of periodicity is very common in natural systems, and he's really going to talk about atmospheric flows. And one of the distinguishing features of turbulent flows, and I think I mentioned this in some of the notes in the class we've talked about so far, and instantaneous turbulent flow patterns are so irregular, attention is often confined to the statistics of turbulence, which are in contrast to the details of a well-organized manner. After he writes this, he talks about short-term and long-term weather forecasting. And if we have a simplified model of the weather, and it's deterministic, even then we have trouble predicting long-term forecasts. Even if we knew all the exact equations for weather, chemistry, and everything, it would be very difficult. I think good papers are written like problem solution benefit. In this paper, he's kind of followed that format and saying, here's the problem physically, and that turbulent flows are highly chaotic, and even if you think they are deterministic, which I would agree with, it's very hard to predict long-term behavior deterministically because of the chaos and sensitivity of the equations. This paragraph here is talking about what he's going to do exactly in this work. So let's look at the first sentence. It says, in this study, I love those words, we shall work with systems of deterministic equations which are idealizations of hydrodynamical systems. So he's going to take the equations of motion, he's going to put them in as a stream function and temperature equation, and then he's going to simplify them. And we're not going to show all those steps because we're here to study and understand chaos and sensitivity. Down here, he notes that the governing laws are expressed as a set of partial differential equations containing the quantities of velocity, density, pressure, and of course temperature, etc., closed form. And that's what we're going to look at. So partial differential equations, which is how we're forming and casting our equations. Going through all that, if you will, I think I picked out another important detail. And he says, in this work, we'll deal with specifically finite systems of deterministic ordinary differential equations, and they represent a forced dissipative hydrodynamical system. So he's not going to look at the full Navier-Stokes equations or Euler equations or any nonlinear fluid dynamic equations. He's going to look at a reduced set of equations. And the reason he's doing that, he's trying to simplify the problem to only its most essential parts, to illustrate the idea of why nonlinear equations are difficult, of course, but also to really illustrate the deterministic nature and how these change over long periods due to small changes. And it's also a set of differential equations, and only 3. And the reason is because differential equations are a lot easier to examine solutions of than partial differential equations. Here, I think, is a really important thing. Well, first of all, solutions to even these representative equations are not known or may not exist. But he says, in linear equations, constant forcing leads to constant response. And that's not true necessarily at all for nonlinear equations. And this is one reason he's basically saying he's not going to study the linear problem. But we can use linear stability theory to analyze it. So we are not linear. And the conclusions in this paper are, of course, not applicable to the linear equations. I've highlighted this part of the paper too. It says exact periodic solutions of simplified systems of equations representing dissipative flow of constant thermal forcing have been obtained analytically by this author, the author of this paper, writer, that's Lorenz. And he's also done this for non-periodic solutions only by numerical means. Okay, so there's basically no analytical solutions, and he's tried to find them. I'm sure a lot of people have tried to find them for this basic simple of 3 differential equations, but nobody's done that, so we have to do it numerically. Now there's such a thing called phase space. And before I go into phase space, I just want to ask the class, has anybody heard of a hodograph? Yeah, a few people. One. Okay. What's a hodograph anyway?
Isn't a mapping of physical space to a frequency space?
Yeah, it's one mapping of, say, physical space to another space. Typically, it's done from physical space to velocity. And if anybody's taken my compressible flow class, I showed shock polars. And shock polars are actually a type of hodograph, because on the x and y axis, you have u and v respectively. So some of you have actually seen them and may not have known it. In this case, when he's talking about phase space, he's really trying to convert the system into another space. And up here, I note that each point in the phase space represents a possible instantaneous state of the system. And for those of you who've heard of the butterfly effect, when you plot these solutions, they appear as kind of pretty butterflies in phase space. So I'm going to repeat those solutions. And that's why the media actually picked up on this paper, and they made movies and everything. They say, hey, if a butterfly flaps its wings in Brazil, a hurricane forms off of Africa. So small changes in the atmosphere create big changes much later that are maybe not apparent easily. Anyway, this section here is all talking about some of these physics and phase space, which I don't want to get too far into, but I recommend reading it as it's a class handout. Section 3, I think, is really important. It says the instability of non-periodic flow. So non-periodic flow is just chaotic flow, and you'll see his solutions in a second. And I think I highlighted this sentence in my own copy. He says, we shall establish one of the most important properties of deterministic non-periodic flow, that its instability with respect to modifications of small amplitude. And so he's really looking at the Rayleigh property. The Rayleigh number is a non-dimensional number, and it dictates, just like Reynolds number, if something is unstable or not. And he's going to go through the equations to define the exact Rayleigh number and set the initial conditions to be just above the onset of instability of this flow for a simple atmospheric layer. And by doing that, he will go into this non-periodic unstable flow regime. So let's go down here, and he says a trajectory P, that's the trajectory of the solution, will be at a stable point if the trajectories in phase space remain near that point. So that's what he means by a stable flow, that in phase space, the vector of solution will orbit or be very close to a stable point. And here the stable point in the flow is the steady solution. And we'll see in these simple differential equations that the steady solution is actually corresponding to the stable flow. Unstable flow means that our phase space solution, that's like the vector of the solution, will be orbiting multiple stable points, seemingly in random, but that's what intermittency is. We will intermittently go back and forth between multiple stable points. And here he defines what a steady flow is. To one point, this is the definition of stability that's familiar with a steady flow. So what would be equivalent in the Navier-Stokes laminar flow solution? So you have a Couette flow. That would be considered a stable, steady flow, laminar flow between plates, right? So what happens if I perturb that solution? It could be unstable and it could transition to turbulence. So this is the analogy. One more thing is here's his definition of periodic and quasi-periodic. Periodic means that you'll be going, say, back and forth between 2 points in a predictable, exact manner, which almost never occurs in these types of systems when nonlinear. And of course, the title is non-periodic. A trajectory which is not quasi-periodic will be called periodic. It's that simple. So if you're in none of those other cases, then you're in quasi-periodic. And we'll look at what that means in a second. On this page, on 133, I wrote, and I highlighted this whole paragraph, which I thought was important to read to the class, because I know not everybody reads the paper. It says, these results will have far-reaching consequences when the system being considered is an observable non-periodic system, meaning turbulent, whose future state we may desire to predict, which is very difficult. Implies that two states differing by imperceptible amounts may eventually evolve into two considerably different states. So that sentence means if I have an initial condition in my equations, and they're almost exactly the same, but maybe differ by a small amount epsilon, will remain exactly the same solutions for, say, 10 or 12 days. But in 10 or 12 days later from this initial condition, they will be completely different. And it's very hard to predict that, but that's what we'll do. Anyway, if there's any error whatsoever in the observed of the present state in any real system, such errors seem inevitable, and acceptable predictions of instantaneous states in the far future will be impossible. And this is really a strong statement because it is really talking about weather prediction. That even if we are able to measure the entire state of the atmosphere at one time and try and integrate that system in time deterministically with a set of equations, it still may be impossible to predict the future because of small differences in the initial condition. And that's where I designed this homework for you. That's all the physics and philosophy. Now, this is where he's talking about his numerical technique. And we're going to do something a little bit simpler. So I'll talk about how we're going to do it, because you'll notice this date of the paper is a lot earlier, and we have a little bit better tools. So all this is numerical theory, and I'm going to outline how I'd like you to try it to keep it a little bit simpler. Okay, so this goes back to a simpler equation by Saltzman, and he says we're going to introduce a system of three ordinary differential equations whose solutions afford the simplest example of deterministic non-periodic flows. And he actually makes it a little bit simpler than the original system that Saltzman gave. And he calls them finite amplitude convection equations to model atmospheric convention. Here's these basic equations. So these are not Navier-Stokes, but you have a stream function. And that's psi, and you have a temperature. And in these communities, it's not uncommon for people to call temperature theta. It's actually a temperature about the mean temperature or atmospheric, uniform temperature. It's theta because it's T, theta, T. Anyway, this is your set of equations, which can be reduced by the governing equations. And it so happens that all these constants are defined right in here, where you have gravity We have viscosity, and coefficients like that. Anyway, you can recover the velocity variables from the stream function, right? U equals partial u partial x, v equals negative, excuse me, how's this go? Psi equals partial u partial x, and negative partial v partial y is psi 2, right? From continuity. Boy, I need to get more sleep maybe. Anyway, it is a long class. Anyway, from these equations, you can actually show there's a stability parameter, which is the Rayleigh equation right there, and that's a Rayleigh number. And if our conditions exceed the Rayleigh number, it's unstable. If it is below the Rayleigh number, by plugging these properties like gravity, viscosity, etc., temperature difference across the top and bottom of the layer, then it'd be stable. So this is how you see those convections. Anyway, this guy here, Saltzman, before this paper, derived a set of ordinary differential equations that simplify these. And that's what this whole section is, and that's all discussed here. And so you can read that if you want and go through it. That's not what is the most important thing. The most important thing to understand this is that those equations here, 17 and 18, have been reduced through all this analysis into 3 ODEs. X dot, y dot, z dot equals negative, oh my god, what's this non-dimensional variable? Sigma? That's, yeah, sigma, boy. X plus sigma y, and negative xc plus rx minus y, and xy minus bz. And these are defined here, these coefficients. So b, sigma, r are just constant coefficients. Like, for example, r is the Prandtl number. And so we can set these really to whatever we want and then study the numerical solutions of the system. But if you solve this set of ODEs, you can backtrack and recover, of course, psi and theta, and then recover the velocity field and pressure and temperature. So that's the big picture of the process. And so we'll be focusing on these 3 differential equations. So anyway, the physical explanation of these equations are put in this paragraph. It says, in these equations, x is proportional to the intensity of the convective motion, y is proportional to the temperature difference between the ascending and descending currents, and it goes on about x and y denoting that warm fluid is rising, cold fluid is descending. Variable z is proportional to the distortion of the vertical temperature profile, okay, from linear A. So that goes as like theta. And he goes through this and identifies parameters for these differential equations where it's stable and unstable using linear stability theory. Okay, so that's not the most important thing, because we're not going to do linear stability theory or worry about that. We're always going to analyze the equations when they're unstable, because we don't care about laminar flow. That's easy. Okay, we care about the turbulent flow. Anyway, if you are curious about that, he defines the critical Reynolds Rayleigh number, excuse me, right here. And you can look at how to do that. Anyway, this is where he presents his numerical results for this equation. And that's in this table. So here's his like initial condition and his iteration in this direction. And then here's his values x, y, and z. And he just gave you these as a numerical example for a number of iterations all the way to 2962. Oh, excuse me, 5948, this n. That's really what we're going to be doing. And let's look at some of his results. So figure 1 is his time domain results. It says numerical solution of convection equations. Graph of y is a function of time for first 1,000 iterations. So here's iteration 0 all the way through 1,000. And, excuse me, this is 1,000, 2,000, 3,000. So here's the initial condition. And this is a plot of y, which is the second variable in the ODE, right here in 26. And you can see it rose up to some value and came down and was orbiting some strange attractor. And it kept going, it was growing, growing, growing. And all of a sudden it starts going into another motion, and there's another strange attractor up here. And now it's an intermittent flow where it's going from top to bottom, etc. And it's seemingly at random. But of course it's governed by these differential equations, which are nonlinear. So without seeing the numerical solution, is there a way to predict, say, the amount of time it spends at one attractor or another, or where it will be at certain times t? The answer is likely no, that we have no way to predict the intermittency or any other type of property without doing the numerical solution. Let's look at these plots in phase space. So here's the graph where we're plotting now the solution, one solution on the y-axis and the other one on the x-axis. And he did negative x, just for the sake of, I guess, aesthetics. I don't really know why. And then here's the two attractors. So you can see up here there's some numbers, and these correspond to particular points in time. So and the curve represents one particular solution based on one set of initial conditions. So if I plot my solution, x and y, right, the unknown variables, and parameterize across t, I'll get these types of curves. And if you squint and look a little and add colors, you might see butterflies, which is, I guess, where a pop culture term came from. But you can see these are orbiting points C and C prime. If I initially started at C or C prime, those would correspond to steady flows. Or if you look at my equations and I set the initial conditions to 0, nothing would ever happen. So there's actually 3 trivial solutions, which are shown in the paper, and they correspond to these 3 points, and they're also the attractors. And you might imagine that this solution, or this whole system, is actually orbiting these attractors in this domain. And so if I could actually draw those attractors, they would be something like this. One would be C prime, and the other one would be, say, C. So you see, for the first 1,000 iterations, we really never really around C prime. We were always in this, I might have them reversed, sorry, but we were always in this domain here. So I guess I have them backwards. Excuse me. So that's interesting. And that's what phase space is. Phase space is really the plot of, like, the unknown variable positions. Those are the major points I'm going to show in the paper. Now let me bring up the homework assignment for you. Project 1 notes. And this is exactly what I've given out in the class assignment. So let's just look at this together. We have another few minutes in class to do this. The Lorentz system, I've rewritten the differential equations for you directly from the paper. X prime, Y prime, Z prime. And remember, these are nothing but, say, partial X, partial T, partial Y, partial T, partial Z, partial T. So those are the time derivatives. And, well, it's really tau, excuse me. T, tau, it's not going to matter here, non-dimensional time. X, Y, and Z are the dependent variables. And I am asking you to solve these differential equations numerically with these coefficients. And these are the ones exactly from Lorenz paper where the Rayleigh number is slightly unstable and where the linear instability theory is applicable. And I ask you to march in 3,000 iterations, just like Lorenz did, using non-dimensional time step of 0.01. So you have a time step, you have a number of iterations, you have the constants for unstability Rayleigh flow, and you have the amazing power of a programming language of your choice, really. And I would like you to march in time using the 4th order Runge-Kutta scheme, which is way simpler than what Lorenz did in his career. And I've also given you an initial condition. X0, Y1, Z0, 0. The solution you should get should be exactly the one, or very close to it, as Lorenz's paper. In fact, when you look at your temporal solution, you can say at long time periods, even though I'm solving the same equations using a method which is roughly the same order, but a different integration scheme, will I have the same answer? The answer is probably no. So you're solving the same equations, same order, same initial conditions, and at 3,000 iterations, you're not going to have the same answer. Why? You had different truncation error in your computers versus his at MIT 50 years ago. Okay, so that's step 1. Repeat what he did. And this is where I would like you to submit what you got in a PDF file to Canvas in 2 weeks. And I just want a short 1 page or less description of the problem, what equations, the numerical solution approach, and discussion of the solution. So I've already given that all to you. And I ask you just some basic questions, like where are the attractors in the flow? And I ask you some philosophical questions. Is it possible to predict or measure these types of turbulent flows in a deterministic way given the sensitivity of initial conditions? And before you answer that question, you'll have to try the plots. I ask you, why do solutions go back and forth from one attractor to another? That's a very curious question. If I'm orbiting one attractor, why would I just go to the other one? Can the times the orbits change be predicted without resorting to numerical methods? That's a very difficult question to answer. Can their frequency? And what can and can't be measured or predicted? So I'm not looking for long mathematical analysis if you want. I'm looking for your opinions, and based on the writing of this paper and your numerical predictions, if there are ways of doing this. So here's really where the homework comes in. I say, do these plots. So the first one is plot x tau, y tau, z tau for 3 plots. And I'll show you examples of what you should see. So I'm going to show you the solutions here. And I asked you to create the famous butterfly plots of x versus y and y versus z on 2 separate plots. And they should look a lot like Lorenz's plots. So you can try that. And now here's the interesting part. This is going to make you really puzzled. I say repeat the calculation by changing the initial condition to this. So x will still be 0, z will still be 0. So iteration 0, x0, y0. But then I say, instead of y1, I say y plus 1 times 10 to the negative 4th. So now I've taken that initial measurement of the initial condition of my weather system and I've perturbed it. I've added a tiny little thing. The little butterfly flap has changed my initial little velocity to be a tiny bit bigger. Thanks, butterfly. And then I want you to repeat the calculation and plot on one graph y versus y perturbed versus tau. And I ask you, at what time tau does the results apparently diverge? So I have different initial conditions, but I will have seemingly the same results for a long period of time. And how long is that? Anyway, this is just what you submit. So, this class is meant for you to concentrate on your PhD research. That's the most important thing. So just reiterate, describe the problem, why it's important, that kind of stuff. Simple. Please don't give me a 20 pages, I won't read it. And just do these plots, reprogram it with Runge-Kutta. And I also ask you to just, as an appendix, copy and paste your computer code, your code. And you can use Python, C, Fortran, MATLAB. I always prefer C or Fortran. But if you want to do Python or MATLAB or whatever R, it's fine. But I don't want you to use like libraries. So I know there's pre-canned Runge-Kutta routines and stuff, but I think it's been a big crime in your education not to have programmed some of these integration schemes. So let's look at, and that's all I need. So here's some of my notes. And I've also put on the class website a paper on Runge-Kutta scheme. And here's the 4th order Runge-Kutta scheme for you. And a Google search for 4th order Runge-Kutta, there'll be thousands of results for this. And you can see it's a completely explicit scheme. So for x, y, and z, I simply find the next value at iteration n plus 1 from the current one. So this is my current known value of n. And h, this is my delta tau, right? Divide by 6, and I have k1, k2, k3, k4, which are defined here. Your function is nothing but the right-hand side of your differential equation for x, y, and z. And then you just loop over that and go from iteration 1 to 3000 and save the results. Plot them. So I'll let people write that if you want, or you can even use a cell phone and take a picture, whatever you want. Has everybody got that, or look it up? Okay, so let's look at what I'm looking for. So here's figure 1.1. This is x versus tau. There's my initial condition, right there. And it looks a heck of a lot like the Lorenz plots, that I was orbiting around C prime for a long time, and I started going periodic back and forth. But you see X and Y look very different. You wouldn't expect them to look the same, but this is just for the initial conditions. So I've repeated Lorenz calculation. Instead of tau, instead of iteration on the x-axis, I put tau, because I like to be in a non-dimensional time, not iteration, which is something for a computer. So these plots are basically repeated. Okay, so you should be able to produce those. Then I went back and I repeated the famous butterfly plots. You see, all I'm doing is plotting y and x. So if you have stored your solution in an array from 1 to 3,000 iterations with the values of x, y, and z in it, you'll be able to easily plot this. This is a Python plot. Okay? Does anybody have any thoughts or questions on how to do that? And we can talk more on Thursday or a week from now if anybody has any questions. Okay, the part that's the second butterfly plot, phase plot. And now here's what your solution should look like for the whole point of the assignment, of the sensitivity of initial conditions, the unpredictability, deterministic nature of nonlinear equations. Perturbation. So here I have y versus tau. So this is increasing iteration on the x-axis, right? Here's y. And you can see my initial condition is very close to 1. It's either 1 or 1 plus epsilon. And I've plotted the base solution in black and the perturbed solution as a dashed red line. So let's, this is about 3,000 iterations here. Let's zoom in. Looks exactly the same. So imagine this is a weather system, and this is your non-dimensional turnover time, integral time scale. It's exactly the same. Okay, I go over this way. This is the middle range. You can see I have huge peaks, inflections, lower peaks, minimums. And so for the second mid part of the range, it's the same. Now let's go over here about non-dimensional time, 28 seconds in the Rayleigh flow. And oh, well, now I can start to see some difference. And all of a sudden something happens near the end of the simulation, about 29 time scales, where the original initial condition is up here at one attractor, C, and the other one is down here at the other attractor, C prime. And it's not impossible, but it's unphysically, like very unlikely, like astronomically unlikely that these solutions would ever return and be the same again. So you can think of it this way. If I knew all the equations for the atmosphere, or even a simple Rayleigh flow like this between like two temperature values in a free boundary, and I measured everything in the system, I knew all the initial conditions and boundary conditions, and I integrated that out, 10 or 20 days from now, things might be very different and are considered unpredictable, even though it's deterministic. That's very interesting to think about philosophically. So anyway, this is what your final plot should kind of look like if you've done it exactly correctly, I think. But my solution might be a little bit different because I was running on a Intel processor using open source Fortran from a 2013 Mac Pro. And it should run in seconds, really. Okay. So what does your program probably look like? Let's talk about that for a second. If we have a few more minutes, because I think it's important. So I think in my program, what I would do is I would initialize my program, right? Allocate arrays, set variables, right? Including the initial condition. And so then I would say like at n equals 0, right? I have x equals 0, y equals 1, and z equals 0. Then what do? I have a loop for n equals 1 to, say, 3,000, an end loop. And I would put in here my Runge-Kutta fourth order integration. at the end of the loop, I would write it to file, write x, y, z to file, and my plots. So that's a simple overview of what I think the program would probably look like if I wrote it. And there's probably other ways to do that. And this wrench cut algorithm here is the one I displayed on the board a few minutes ago. But basic in here, right, you want to say n new equals n plus 1 essentially. And you would say x new, y new, z new equals the right-hand side of each individual equation. And you would get these new values based on your Wrench-Kutta method, because you would have like n equals n plus 1, and you would basically store your result in a large array from 1 to 1,000, or 3,000, excuse me. And the right-hand sides, of course, are on your assignment, which is equations 11.1, 11.2, and 11.3. Those are the three right-hand sides, right? Alex?
I'm wondering what precision did you use for your codes? Just double precision?
Yes. So that's a great question, and I'll repeat it from my notes and recording, is what precision did I use? Well, that's a great thought. Generally, you want to use as much precision as possible in these types of simple scientific calculations. I used basically double precision. If you write in C or Fortran, you'll have a lot of control over this, and it would be awfully wonderful in life if you could ensure that the precision of your prediction is not going to affect your results. So if you have a low precision code, you'll have error. But I guess the precision I used was good enough to repeat Lorenz's paper, which made me happy. But then you could say, well, what if I have higher order precision than double? Will the results change? I don't know. It's a good thing to check, I guess. It's a great question. Yeah, but I use double precision for my calculations. And if you use, I don't know, in MATLAB, can you control precision? Yeah, okay. Okay, other questions? Probably see a few nervous faces. Some of you, this might be super trivial, and some of you will be really difficult. And that's okay, because there's all kinds of different students here. But hey, you'll have written your own first CFD solver. This is technically a CFD solver because you're solving fluid dynamic equations with a computer. That's the very definition of CFD, numerics. Okay, any other questions? Okay, well, I'll let you go, and thank you so much for your time today. And